Okay, this is the example we did in class today of a multi-level projectile, where you have a projectile that is launched at a certain angle and doesn't just land at the same height that it was launched at, but continues down a little lower. Now, the same type of setup would be used if we were doing an example where it was shot from lower and landed higher, but we'll deal with this one for right now. So we have a projectile that's launched. This is the one that we launched in class and attempted. Launched at 6.35 meters per second of a velocity at an angle of 45 degrees. And it was a height of 1.087 meters above the ground. So this was the floor, and then the launcher itself from where the ball was released was 1.087 meters. So we set it to 45 degrees. We saw that by the protractor that was hanging down from the launcher. It let us know that it was at 45 degrees. And we pushed this ball back 3 settings to the fastest setting with the ramrod, and then the trigger pulled back to release the ball on its path. So, to start out, we had 108.7 centimeters of height right here, and we converted that to meters because we're dealing with our velocities in meters. So, that's the initial setup. To do this problem, we're going to deal with it in 2 stages, because this dx right here, this one right here, is different from this dx. But these two, this one here and this one here, are equal. So we're going to deal with this in 2 stages. First will be the rising, then will be the falling. Okay, so let's go to the next picture and continue. So to deal with the rising part, from where it was launched up to the peak, remember, there is more to this landing that goes below it, okay, but we're only dealing with from the launch to the peak. So this ball was launched, goes to the peak from launch height. We're disregarding that initial 1.087 meters of height. So it's launched at a velocity of 6.35 meters per second and an angle of 45 degrees. So the first thing we want to do is find the components of this velocity. So here's the actual velocity right here that the ball is going to be launched at. We want to find an x component and a y component for this velocity at 45 degrees. So by translating this y vector over to here, making it into a triangle, we now have Vx equals v cosine theta, which we get to be a Vx of 4.49 meters per second. And the same for the sine because it's opposite and hypotenuse. So Vy over V, and if I multiply both sides by V, it comes over, and I have this setup, which gives me a Vy of 4.49. Now, throughout this problem, we chose a 45 degree angle to make it easier so that these two would have the same number. But during a regular problem, these will be different numbers, so you want to keep track of them. So the next thing that we're going to do is we're going to deal with, I'm actually going to draw this part, we're going to deal with this problem not necessarily as the rising part, but kind of also as if it was falling. So from here, if it was falling back to this height, we're going to deal with it kind of like that, because then we can use that formula Vy equals Vi plus Gt, where Vi equals 0. We can use that formula now to solve this, and it becomes Vy equals Gt. So I'm going to deal with that initial Vy as if it was the Vy here falling. So Vy equals Gt will calculate the time from here to, and we're falling, to here. So, and we're falling. So I do Vy equals Gt, and I get a time of 0.46 seconds. Now that 0.46 seconds is either rising or falling. Doesn't matter. It's going to do the same thing for us. So from there I can plug it into the dy1 equals 1/2 gt squared formula. The dy1 was this height right here. We call it dy1 because in the initial problem the whole dy was dy. The whole height was dy. This is dy1, just this height. So dy1 will equal 1.04 meters, and then we plug in the same time to the dx1 equals vx times t. Vx, remember, was this horizontal velocity, and this dx times vx equals vx times t will give us this horizontal distance, so from where it launched to the peak. And in the original problem I had that drawn lower, but that was this initial horizontal distance. And that, when we plug it in, comes to 2.07 meters. We're going to need this stuff later on. But remember the steps: components, drop time, drop height, total distance traveled for just the rising part. For this next part, we're going to deal with the falling part of it, from the peak all the way down to the bottom. The rising part we actually used from the peak to here, to the same level as the initial launch, to do some of our calculations. But now we're going to go past that. We're going to go down to the bottom where the floor was. This was the initial dx that we calculated over here, but we can't use that because, as you notice, there's a little more x displacement on the bottom because of the extra time to fall. So what we have to do now is start over as a new, almost like a horizontally launched projectile, where the horizontal velocity Vx is up here, and here's our drop distance, and we can find our time variables and things from there. So to find our new peak height, we're going to take dy, which was the initial height of the launcher from the floor to the launcher that was on the table, and we're going to add our dy1, which is the new height from the angled launch that the ball gained on top of its initial height. It gained this extra height from being launched. We add those together, 1.087 and 1.04, and we get 2.127, which is the total height that this ball will have to fall on its downward motion. So now that we have this total height, we can calculate the free fall time from the peak down to the bottom. That's by using, we're going to call it dy2 now, which is the total drop from top to bottom. So dy2 equals 1/2 gt squared. I plug in the new dy2, and I get a time for free fall of 0.659 seconds, which was longer than the original rising, which is good because it had extra time to fall. Now I can take that free fall time and plug it in with my x component from the original motion, because the x velocity does not change throughout the entire problem. I can plug that in with my x velocity, 4.49, and the 0.659 to get a dx2 of 2.96 meters. That's the second part, not the little bit, but the little bit plus the extra, so it's from the peak down. Now that I have the initial dx1 and the new dx2, I can add those two together to get a total dx of 5.03 meters, which is about 503 centimeters. Now, in the experiment that we did in class, we actually measured it out when we put the carbon paper on the floor with the paper underneath it, and we marked where it actually fell. We actually got a total displacement of 483 centimeters, or 4.83 meters. And what we calculated from the original velocity was 5.03 meters. So obviously something is off, and I'm willing to bet that it's the velocity in the beginning is just a little too fast, which is something that I guesstimated off the hip from past experience with this launcher, but it may not have been exactly accurate, but close enough. So what you get out of this is a step-by-step process of how to calculate a multi-level problem like this. Now, the only difference is if you were to be launching from a lower height and landing at a higher height, for instance this, like if this is where I'm launching from and I'm landing somewhere up on top of like a table, for example. Let's say that's a table. The only difference now is that the dy's that we were using, we would still deal with a rising part, which would bring us up to the peak, and then the second part where we added the dy's, in this case we would now subtract this from the little peak height that we found up there. We would subtract the two. Subtract this table height from the total height to get the new peak height, which we would then use to find the falling part. So that's the only difference, is that you find a total dy first and then subtract the table, whereas in this case you found just the peak and added it to the table. That's the only difference for changing it in that way. I would definitely get these steps down one after another, so on the test when you're asked just the basic information, you're given a velocity, an angle, and a table height, you'll be able to go through and calculate total horizontal displacement or total peak height for this type of problem.